Welcome to this second in the series of Epicor webinars. My name is Kevin Hewitt and I work as a Senior Solutions Engineer for Epicor in the UK. This webinar will review some of the key functionality available within the Epicor ERP Planning and Scheduling modules, and will cover an introduction to the core concepts and then look in more detail at scheduling, material requirement planning and capable to promise. In order to understand the depth and breadth of planning and scheduling functionality available with Epicor ERP, it is first of all necessary to understand a few of its core concepts. The planning and scheduling modules available cater for both project management and manufacturing requirements. The flexibility and agility available within these modules allows Epicor ERP to support multiple business process flows simultaneously, ranging from make to stock through to engineer to order, and to vary the flow for a transaction on the fly. This webinar will focus on the manufacturing, planning and scheduling aspects of this functionality. At the core of Epicor ERP is the MRP II process. MRP II uses the Epicor scheduling engine to schedule planned jobs in order to determine start and end dates and hence lead times, rather than assume a fixed lead time offset. It is possible to deploy either an infinite or a finite scheduling algorithm at the time of MRP II execution. Infinite scheduling calculates the dynamic lead time, i.e. the lead time is job quantity dependent. Finite scheduling calculates a dynamic and capacity constrained lead time, where the lead time varies with how heavily loaded resources are. In general terms, the larger the batch size and or the more loaded resources are, the longer the lead time. The sophistication of the scheduling logic available to the MRP II process is dependent on which of the Epicor ERP scheduling engines is used. The standard engine allows for a maximum of 2 resources to be defined against each operation. For example, a machine and a labour resource. It does not permit material unavailability to influence the outcome of the scheduling calculation. However, the Advanced Planning and Scheduling APS engine allows an unlimited number of resources to be attached to each operation and allows material constraints to impact on the calculated schedule. With the APS engine, it is possible to elect to run MRP infinitely or finitely, and with or without material constraints enabled. This allows the relative scheduling impact of capacity and material constraints to be identified. With material constraints enabled, the supply lead time of unavailable materials is incorporated into the scheduling lead time for a job. This will push out the scheduled start and end dates of all sub-assemblies on the critical path and elongate the lead time. The reason that this logic can be supported by the scheduling engine is due to the structure of the method of manufacture, a combined BOM and route defined in the engineering module. Methods of manufacture, primary or alternate, are defined relative to part revisions. Each revision holds the effectivity date at which the revision will be phased in. Each manufacturing site within a company holds a planning method identifier, either the primary or an alternate method, and when the MRP II needs to rate a planned job for the part in the site, it will choose the planning method at the appropriate revision based on the due date of the job. Within the method, materials, components and sub-assemblies are associated with routing steps, so that the scheduled requirement date for each is dependent on the start date of the operation. Each used on part on the method also holds flags that instruct the scheduling engine how that part should be processed when a job is raised from the parent. For a manufactured used on part, the options are puller's assembly, which means that the planning method of the child part will be incorporated into the parent method on a lot-for-lot basis, or planner's assembly, which works in a similar manner but uses the MRP policy parameters to determine the production quantity for the child sub-assembly. The implication of pull and planner's assembly flags is that MRP II will raise a multi-level job. The difference between poor and planned as assembly multi-level jobs can be illustrated by the methods for parts A, C and D. A requires 1 C, while C requires 2 E's. If C and E are flagged as pull as assembly, then an order for 10 of a part A will result in a multi-level job in which the sub-assemblies C and E are inserted into the job for A with a lot-for-lot production requirement of 10 and 20 respectively. The MRP II process will not take into account any stock of C and E unless a flag is set on the planning parameters for this automatic consumption. C and E will be released to manufacturing as part of the same job as part A. The job traveller for the job will produce a separate sheet for each sub-assembly. C and E will not be booked into stock and reissued, they will simply be tracked to completion within the job for part A. This setup is typically used in an assemble to order or make to order environment where stock is not planned. If C and E are flagged as planned as assembly and hold an MRP lot size policy of multiples of 15, then an order for 20 of part A will result in sub-assembly quantities of 30 and 60 respectively for C and E. The overrun quantities for each part will be automatically taken into account and consumed by MRP when planning additional demands for C and E. When C and E are released to manufacturing, they are released as separate jobs and are booked into stock and then issued to the job for the next level above. This setup is typically used in a make-to-stock environment. From the perspective of material capacity constraints, the existence of the multi-level job allows any constraint to impact on the entire schedule of all the sub-assemblies within the job up to the top level. There is one other relationship that can be defined for used-on manufactured parts on a method. A used-on part can be flagged as non-stock in a site. When a non-stock part is not defined as pull as assembly, then a lot-for-lot hard-ped linked separate job can be raised for the used-on part to supply the material requirement at the next level up. MRP2 only creates linked jobs when the parent job is firmed. This supports a make-to-order environment, but with separate jobs. Once the make-direct job links have been established, scheduling can schedule the group of jobs as a single entity. As a result, if the job for part E moves out due to either a material or a capacity constraint, the jobs for C and A would be automatically pushed out as well. On completion, the used-on part is transferred from its job to the parent job without going in or out of stock. Given the importance of the scheduling engine to the MRP2 process, I will cover this functionality first, starting with an overview of what is available and then look at some of the key aspects in more detail. There are two types of manufacturing jobs supported by scheduling: production jobs generated by MRP or directly from a sales order in job shop environments, and maintenance jobs which are generated by preventative maintenance schedules or repair requests for equipment. The scheduling calculation will schedule these jobs in either infinite or finite mode and will update the shop load versus capacity position in real time. Once the schedule has been calculated, a master scheduler can trial alternative what-if scenarios through the use of scheduling boards, rescheduling individual jobs, or by globally rescheduling all jobs based on date and priority criteria. These what-if scenarios generate an impact analysis and can be saved and restored as required so that a comparison of the effectiveness of each scenario can be determined. Once the optimal what-if scenario has been arrived at, it can replace the current live schedule. An additional type of what-if scenario is available with APS called Capable to Promise. CTP is an MRP2 or trial kit simulation for the demand associated with a specific sales order. It determines whether the order demand can be manufactured in time to meet the required ship-by dates and highlights where and the reasons why this might not be the case. Shop floor resources that are associated with operations are structured hierarchically by site, department, resource group or work center, and specific resource. Calendars of working days and working patterns are inherited down this hierarchy automatically, but can be overridden at either the resource group or resource levels. Resources can be set up to be either time-constrained, in which case the working days and pattern on the calendar define their capacity, or daily production quantity constrained, which means that they can only process so many units per day, or that they are concurrent capacity constrained, which means that at any point in time they can only process up to a specific volume, area, or amount of material associated with productions. A good example of this might be a kiln, which may have a cubic capacity constraint on the items it can contain. Calendar exceptions are non-working periods such as holidays or sickness, or additional overtime, and these can be added to resource calendars to flex the capacity available for the resource. A wide range of parameters can be defined to influence the behavior of the scheduling engine. At the company level, there are flags that denote if scheduling before the current system date and time is allowed, and how load will be relieved by shop floor data capture, either by quantity completion or by the time booked, and whether global rescheduling can reschedule started operations. At the site level, the capacity planning horizon is used to determine how far into the future resource load should be calculated. The overload horizon is used by infinite scheduling to determine how far into the future to report overload conditions. Full start and or end time flags synchronize overlapping operation start and end times. Override constraints determines whether the master scheduler can override capacity and or material constraints in what is scheduling. And the enable multi-linked job scheduling allows make direct link jobs to be scheduled as a group. At the resource level, finite scheduling can be enabled, and the finite horizon determines how far into the future in days that a finite schedule should be calculated for this resource. The minimum overload percentage determines the point at which overload will be reported. Queue and move times for this resource can be entered in hours. These will be added to all operations scheduled on this resource. Split operations allows the work associated with an operation to be split evenly over the resources in a resource group, with each split being separately scheduled on each resource. At the job level, the job priority code is used by global rescheduling to determine the job scheduling sequence. It also defines whether the scheduling direction is forwards and backwards, and if WIP should be minimized. At the job operation level, set and run times and production quantity yield factors can be set in an appropriate unit of measure. Scheduling blocks defines the number of complete set of resources required for the operation. Operation overlapping rules refer to send ahead quantities and successor operation start and end date policies. And subcontract operation days outside indicates the duration that WIP will be outside the site when a subcontract process is being performed. At the capability level, capabilities are available with APS. They represent skills rather than identify a resource requirement for an operation. The routing step can hold capabilities. The scheduling algorithm will find the best placed resource to perform the skill and adjust set and run times based on the proficiency of the resource. Finally, at the job material level, buy direct lead time is used and is set when materials are flagged to be bought direct to a job rather than to stock, so that this lead time can be built into the schedule. The default lead time comes from the supplier lead time for the part. Once these parameters and capacity settings have been defined, then MRP2 and global rescheduling may be run to generate live production schedules and a capacity plan. If MRP2 is run in infinite mode, then the scheduling engine will ignore any finite horizon defined for each resource. Dependent on load, there is often then the potential for overload on resources at any point within the capacity planning horizon. If MRP2 is run in finite mode, then scheduling will be bound by the capacity constraints defined for a resource within its finite horizon. As a result, operations will be pushed out to ensure that capacity is not loaded, which will result in later jobs and delayed shipments to customers. Another approach to capacity planning is to run MRP2 infinitely, and then to run global rescheduling, finitely in what-if mode. Global rescheduling reschedules all jobs based on the degree of expected lateness and priority sequence, and will provide a picture of the likely lateness that can be expected if additional capacity is not added to remove the overload position. There are two ways in which the scheduling engine can schedule operations across multiple resources. The first is through the use of scheduling blocks defined against an operation. Each operation holds a list of the resources needed to perform an operation in terms of both setup and runtime. This group of resources represents a scheduling block. When multiple blocks are specified, then the scheduling engine must find available resources for each block and then schedule and load each block independently. The second way is through the use of operation splitting defined against a resource group. This is used when the resource group is the sole resource specified in the scheduling block. The scheduling engine automatically splits the production quantity of an operation across the number of resources in the group and then schedules each split independently. This has the effect of spreading the work associated with an operation over the resources and reduces the elapsed time of the operation in the schedule. Operation overlap rules may be defined between operations on the routing of a method of manufacture through the use of send-ahead and successor operation start and end parameters. The send-ahead quantity is set on the predecessor operation, either in the form of an elapsed time, an absolute quantity, or a percentage of the job quantity. The scheduling engine converts the elapsed time send-ahead into a quantity based on the runtime of the operation. The successor operation holds the start or finish relationship that is required between the two operations. How this is set is dependent on the cycle time of the successor operation relative to the predecessor. When the successor has a greater or equal cycle time, then typically a start-to-start relationship is specified. The successor operation will start after the scheduling engine has calculated the time taken to produce the first send-ahead quantity. When the successor operation has a shorter cycle time, then typically a finish-to-finish relationship is specified. The successor operation will be scheduled to finish after the duration of the elapsed time of the send-ahead quantity is added to the finish of the predecessor. The start time is set by subtracting the duration of the second operation from the calculated finish time. However, this calculation can be further modified by the site-level settings that allow either the start and or the end times of operations with overlap rules to be set to the same values. This prevents additional work being scheduled on the overlap resources to prevent any delay. The purpose of Minimise WIP scheduling is to remove the gaps that occur between operations in a finite scheduling context when capacity constraints exist. This type of scheduling performs a backwards, forwards, and then backwards again schedule of the job in order to minimize the gaps between operations as much as possible. As a result, the elapsed time of a job in WIP is kept to a minimum. This type of scheduling is enabled via the priority code that is assigned to a job. As outlined in the coverage of course concepts, multi-link job scheduling can be performed once make direct jobs have been linked together. It enables any movement in one job in the chain to impact on the predecessor and successor jobs in the chain. This type of scheduling is enabled via site-level parameters. However, the master scheduler can override this setting in all job scheduling contexts. Unlike all the other scheduling engine features that have just been covered, capability-based scheduling is only available with the APS scheduling engine. It enables scheduling to dynamically adjust the route of a job. Capabilities can be thought of as skills or competencies that are possessed by any type of resource. When a resource is linked to a capability, the following parameters must be defined for the resource. A sequence number that denotes the order in which the scheduling engine will check for the availability of a resource when determining which resource to use, and set up a runtime multipliers that represent the resource's proficiency at the capability. For example, the proficiency of 1.25 would extend the standard operation time by a quarter. Capability scheduling is triggered when a capability is referenced in the scheduling block of an operation instead of a resource. The scheduling engine then uses the resource list tied to the capability to find the most preferred resource that is available, and then adjust operation times in accordance with the proficiency of the resource. When MRP2 or any rescheduling process has been run, the impact of the scheduling change can be viewed by the Master Scheduler's Workbench. This is the key screen for a Master Scheduler, as it pulls together all the information needed to perform this important role within a manufacturing company. This workbench provides visibility of the on-time, early or late status of jobs. It also shows MRP new jobs and change job suggestions. It allows the viewing of the job operation schedule for a specific job, and the pegging of a job to its lower level jobs and purchase orders, or for a sales order. It shows capacity planning and load graphs, and what-if scheduling impact analysis. Plus, it provides access to the key scheduling processes through the job, resource, and multi-resource scheduling boards, and global rescheduling. The capacity V load graphs available within the workbench allow the master scheduler to see where their capacity constraints are. The supported views are the overload informer, which shows the degree of overload per day on each resource across the planning horizon, the departmental load versus capacity graph, which can be looked at either by resource group or by resource group by week and by day. The resource group and resource load versus capacity graph can also be shown by day and by week, all the load versus capacity on all the resource constraint types, such as time, daily production quantity, and concurrent capacity. The what-if scheduling boards provide the master scheduler with the tools necessary to move around jobs and operations and simulate the schedule impact of these movements without updating the live production schedule. There are 3 different types of scheduling board available. The job scheduling board allows jobs to be resequenced or operations to be moved within jobs. The what-if schedule dates for the job may then be locked in place in the schedule. This allows the master scheduler to fix where key jobs should be placed in the production schedule, and global what-if rescheduling will then reschedule all other jobs around these key jobs. The resource scheduling board allows the master scheduler to create an optimal operation sequence for a specific resource. Key to this is the use of load leveling of operations. The multi-resource scheduling board allows the master scheduler to move operations between resources. The impact of the what-if adjustment is immediately visible on the master scheduler's workbench. This allows the effectiveness of any change to be assessed. Whenever a what-if scheduling adjustment is made to an operation on a job, or to a job itself through the scheduling boards, the master scheduler can select what impact the adjustment should have over all the other operations with the job across multi-level sub-assemblies within the job. The options available are to reschedule all the operations on the parent assembly and all sub-assemblies, or to reschedule the current operation and all predecessor operations, or reschedule the current operation and all successor operations, or only the operations on the affected sub-assembly. If required, this what-if schedule can be saved, and an alternative what-if scenario can be tested. Saved what-ifs can be restored back as and when required. This allows the impact of different scenarios to be easily compared and contrasted. Once the optimal what-if schedule has been identified, the live schedule can be updated directly from the what-if changes. The what-if impact analyses available within the Master Scheduler's Workbench show the changes that will occur in revenue arising from earlier or later shipments, and the impact on on-time and early jobs that now will be late, and the impact on late jobs that will now be on time or early. The impact on resource group utilization can also be seen via the Change Impact Informer. Resource load leveling is available from the Resource Scheduling Board. It allows all the operations to be pulled together over a user-specified start and end date horizon, and then rescheduled in accordance with a sequencing option, either by setup group priority, operation code, or by date. As a result, gaps in the schedule of work for the resource can be removed, and operations can be sequenced to minimize setup changes. Global what-if rescheduling allows all unlocked jobs within a site to be rescheduled in a sequence determined by their currently scheduled degree of lateness and a multiplier factor associated with their job priority. The process first calculates the rescheduling sequence and then allows the master scheduler to make adjustments to this sequence if required before rescheduling each job in what-if mode around the currently locked jobs. The master scheduler has the option to run global what-if rescheduling in all modes, infinite or finite, and with or without material constraints. The impact of the reschedule can then be visualized on the master scheduler's workbench before being applied to the live system. While the scheduling engine is a key component of MRP2, the Epicor MRP II process also contains important functionality of its own. As with scheduling, I'll provide an overview and then drill into some of the key aspects. The MRP2 process supports a wide range of different manufacturing approaches from make to stock to engineer to order. The process flow that is adopted for a part can be varied on a transaction-by-transaction basis. However, in this webinar, I will be focusing on the make-to-stock process flow, and I will start with sales forecasting and master production scheduling. Independent forecasts can be defined by site, part, and customer. The forecasts consist of dates and associated quantity requirements. This forecast may be either entered manually or automatically uploaded through one of four methods. The Epicor EDI demand management module can receive proposed forecast call-off schedules from a customer relative to a JIT contract via EDI. Once these schedules have been reviewed, they are automatically transferred into independent forecasts for the customer and parts concerned. The Epicor multi-site module also allows purchase suggestions raised in one company to be transferred into the supplying company as forecast. Multiple parts, dates, and quantity combinations may be sent and received through this process. Integrations with third-party statistical forecast applications provide another way of uploading a forecast. Epicor has developed integrations with Smart Forecasts, supplied by Smart Software Inc., and Forecast Pro, supplied by Business Forecast Systems Inc. Sales analysis data can be exported down to these products over a user-defined historical horizon, and the resultant forecast derived from this data can then be re-imported as independent forecast. Finally, a generic file format integration has been developed to allow independent forecasts to be uploaded from a non-integrated forecasting application. Once forecasts have been defined, they can be passed to MRP2 to plan production and procurement to satisfy this demand across all levels in the method of manufacture. Company-wide forecast window parameters, consisting of a number of days offset either side of the forecast date, define how MRP2 consumes forecast arising from sales order and dependent demand. Driving MRP2 from forecast means that the production and procurement plan is driven from expected sales demand. However, production facilities often prefer to build a master production schedule to drive production procurement rather than rely on the accuracy of the forecast. In this case, forecasts may be transferred into the MPS and adjusted manually by production planning before being submitted to MRP2. Unlike forecast, MPS demand is not consumed by sales and dependent demand. In fact, these sources of demand are not taken into consideration when an MPS has been defined. MPS is the only demand considered by MRP2 out to the limit of the MPS data horizon. Outside this date, any imbalance between the MPS-driven supply and actual demand is corrected through the MRP process. The function of the MRP2 process is to balance the supply of each part to the demand that is required. In order to do this, MRP2 requires replenishment policy parameters to be defined at the part site level. The MRP2 calculation can apply either reorder from minimum or economic order quantity multiple type replenishment rules. In the case of reorder from minimum to maximum, the parameters consist of a minimum reorder point, a maximum stock quantity, and safety stock. The safety stock can be netted from stock on hand before other demands are considered. In this context, when the reorder point is reached for a purchased part, a purchase suggestion for the part is raised. If a preferred supplier is defined, then the supplier's lead time and minimum order quantity values for the part are used to determine order buy dates and the replenishment lot size. If there is no preferred supplier, then the part site parameters for lead time and minimum order quantity are used. However, a site-level parameter defines whether safety stock can be consumed by demand in the MRP2 calculation. If this is set, then rather than being netted, should the projected balance in the MRP calculation fall below the safety stock level, then urgent replenishment parameters, also defined at the part site level, kick in and supersede the standard minimum to maximum replenishment rules. These urgent replenishment parameters route the purchase suggestion to an urgent supplier with urgent lead time and minimum order quantity settings. The lot quantity MRP rules supported consist of multiples of economic order quantity within a minimum to maximum lot size range. In addition, days of supply rules can also be applied to these to ensure that the net quantity requirement for so many days into the future is calculated and then adjusted in accordance with the lot multiple rulings. It is possible to define different lot quantity MRP rules for both a short-term horizon and the normal medium to long-term horizon. Plus, for manufactured parts planned via MRP, it is possible to define minimum start quantities for new planned jobs. These kick in over a defined horizon and where there is not sufficient material available to produce the normal lot size. These rules automate job splitting. If there is sufficient material to produce the minimum acceptable lot size, then a planned job will be raised and scheduled for this quantity, and the shortfall relative to demand will be replenished by the short or medium long-term parameters depending on the date in the planning horizon on which the splitting occurs. Epicor ERP provides a workbench for planners that can recalculate minimum, maximum and safety stock levels based on historical usage. All of the parameters of the calculation can be set up by part class or be overridden for an individual part site combination. These parameters consist of the historical usage period, expressed in calendar days, and whether sales and or manufacturing usage should be included in the calculation of the total usage figure. A minimum to maximum stock, a maximum multiplier factor, and a safety stock percentage. The workbench then uses these parameters to calculate the following: the daily stock usage, and from this it can calculate the minimum quantity by multiplying the daily usage by the lead time for the part, and the maximum quantity is then set by multiplying the minimum quantity by the minimum to maximum multiplier. Safety stock is calculated by calculating the minimum quantity multiplied by the safety stock percentage. Planners can choose then to update the current part site values with the newly calculated values as and when required. There are some additional parameters that can also be set at the part site level that influence the behaviour of the MRP II process. These can be divided into two groups, those that affect the lead time and those which affect the volatility of change suggestions generated by the MRP II process. The additional lead time related parameters are defined in days and are passed to the scheduling engine when a new planned job is scheduled. Receive time is the time taken to move a part into stock after it is received. For purchased parts, this is the dock-to-stock lead time. For manufactured parts, this is the time required post-quantity completion to move the parts into an appropriate stocking location. Kit time is the time taken to kit marshal all the parts required for a job so that it can be released to manufacturing. Production preparation buffer is the time taken to set up a production line needed to manufacture the part. When MRP II is run, there's an option to include or exclude this time buffer from the scheduling engine. The volatility dampening parameters consist of a planning time fence, which is a horizon within the MRP run in which MRP cannot make changes to the production schedule. There are reschedule in and out deltas specified in days. A change suggestion will only be raised if the extent of the change falls outside of these deltas. And transaction lock flags can be applied to jobs and purchase orders to prevent purchase or change suggestions being raised to either move in or move out or to change job quantity. The MRP II process can be run at either the company, i.e. all sites level, or at the single site level in one of three distinct modes. Regenerative MRP replans all the parts. Net change replans only those parts where there has been a change in stock or the supply-demand pattern or in the replenishment policy parameters since the last MRP run. MRP by part or product group or part class replans a subset of parts exploding down through all levels of the method below the parts specified in the process. The replanning process generates new planned jobs and purchase suggestions and change suggestions to existing firm and release jobs and purchase orders. Multi-level pegging can be run either as part of the MRP II calculation or as a standalone process. It matches supply transaction to demand transactions right the way through from independent demand to purchase suggestions. In so doing, lateness and or shortness of supply can be picked up and used to calculate the cumulative lateness that each sales order shipment might incur. 3 dashboards are available for planners and buyers to review the result of the pegging process. And the key one, the projected sales order lateness, shows the supply pegging to each sales order shipment and the number of days of lateness expected for each shipment. MRP II recommendations are made available to planners and buyers by workbenches. These present a list of recommendations to the buyer and planner to implement and can be actioned directly from the workbench. This enables the closing of the loop from the MRP process. The final subject to be covered in this webinar is Capable to Promise, called CTP. CTP is only available if the APS scheduling engine is being used. It is used in sales order entry to calculate when it will be possible to deliver goods to the customer and thereby generate an order acknowledgement with promised delivery dates. The CTP calculation is effectively an MRP II or trial kit calculation specific to just the shipments required on a sales order. A CTP job is raised relative to each sales order shipment on a lot-for-lot basis, and the job is then scheduled using the APS scheduling engine. The multi-level puller's assembly and planner's assembly requirements are created within the CT job if stock is not available for the sub-assemblies. For other manufactured and purchased parts, the projected balance available at the scheduled requirement date for the material is checked, and if there is not sufficient quantity to meet the meet the requirement, the lead time of the part is then built into the schedule. The result is the calculation of the expected shipment date for each shipment. When capacity or material constraints exist, this can result in the calculated shipment date being later than the customer's request date. Once all the expected shipment dates for requirements on the sales order have been calculated, it is then possible to adjust the shipment dates through the use of order promising actions. There are two options available. The first is the ship complete option. This will alter the ship by date of all shipments on the order and synchronize each shipment to that of the longest lead time item on the order. The objective being to ship all the requirements on the order together so the order is shipped complete on one shipment. The second is to rerun CTP using the ship partial quantities. This will split each order shipment into two separate shipments when the CTP job cannot be scheduled to meet the customer requirement date. The first shipment will be for the quantity that can be made in time. The remainder will be supplied for a second scheduled CTP job. Once the best delivery dates have been calculated for all shipments, then the CTP jobs for the order can be flagged as confirmed. This will convert the CTP jobs into planned jobs, and the shipment dates on the order will be set so that the sales order can be acknowledged. If you have any questions following reviewing this webinar, then please don't hesitate to contact the Epicor marketing departments in Southeast Asia and Australia and New Zealand. Thank you very much for listening and attending this webinar.